The title of this work is Learning about the Livability of Cities from Young Migrants Using the Combinatorial Hodge Theory Approach. We would like to talk about how migration flows of the young can be transformed, with tools from algebraic topology, into a practical, policy-relevant, livability map for every municipality in Japan. Let's begin by exploring why we're concerned about this topic. Over the last 15 years, Japan's total population has fallen continuously. Just last year, we lost another 800,000 people. This population decrease will accelerate. Therefore, out of 1729 municipalities, 744 are officially at risk of disappearing. The right photograph on the slide symbolizes the hollowing out of many local streets. For city governments, this is an existential threat. Survival now depends on attracting younger residents, families who will pay taxes, start businesses, raise children, and sustain community life. I will provide an overview of my talk at the beginning. Given that challenge, we ask, which places are truly livable for the young? One obvious source of information is actual migration. When somebody relocates, they incur real pecuniary and emotional costs. So, in Charles Taiboot's language, they are voting with their feet. Yet migration data are messy. For any pair of cities, we know how many people moved from I to J and vice versa. But we don't directly observe a single scalar score indicating that city J is 0.8 better than city Y. Our contribution is to extract such hidden scalar metrics by introducing a scalar potential of people flow, which governs unbalanced, acyclic migrations between cities. Using the potential, 1. We estimate a livability score for every municipality for two key groups, women of reproductive age and families with small children. 2. We run regression analyses to see which amenities or labor market features are relevant to those scores. Okay, let me start with a question. Where are livable cities? There are two classic approaches to measuring people's preferences. First, ask people. In your opinion, which city is the most livable? Such surveys are valuable, but they capture perceptions rather than revealed choices. So, we take a second approach. Ask data. Where did you actually move to? The second revealed preference approach is already discussed as voting with their feet, as written here. Internal migration flow is the sum of people's assessments of living places. So in Charles Taiboot's language, they are voting with their feet. This data of people's movements provides stronger evidence of a location's livability than their perceptual evaluations. But there is a technical problem to be solved. The problem is how to quantify such livability from migration data. Technically, our raw data form an origin-destination matrix. The element of the OD matrix tells us the number of migrants from one city to another. This means that the number of persons who voted for city J is better than I. This is data on pairwise comparisons between cities. But what we want is not the pairwise comparison. We want a scalar value of each city to represent its livability score. Therefore, there is a gap between what we can obtain and what we desire. This is a problem. How to quantify a score for each city based on pairwise comparisons between cities? In literature, researchers have tried to answer the problem. Starting from seminal works, researchers focused on some specific quantity of cities and considered their regional differences will drive the pairwise migration flow. For example, these researchers argued on income and job opportunities, and the income differences between cities will explain the migration between them. In other works, the regional utility in the discrete choice model has been estimated directly from interregional migration data. In the model, the differences in utility explain the migration flow. To find the answer, we take another approach by using combinatorial Hodge decomposition. Look at the cartoon network on the slide. Any net flow on the edges can be split uniquely into gradient, harmonic and curl components. We focus on the gradient component. The component is given by the difference of potential. That's what we call livability. The potential extracts the regional differences that reproduce the imbalanced, acyclic component of the given flow. The extracted potential is globally consistent. The value does not depend on paths. The other two components are circular. In these components, incoming and outgoing fluxes are balanced, and they have no impact on the increase or decrease of residents. Formally, take an undirected graph and an skew-symmetric edge flow. Then let us define operators gradient, curl and divergence as in this literature. Here, S denotes the potential. Its regional difference gives gradient flow. The space of the flow matrix is orthogonally decomposed into the images and kernels of these operators. Next, we apply this decomposition to migration data. Migration data is given an OD matrix. We first compute the net flow. The potential is defined as the solution to the following optimization problem. This is simply the weighted least squares, and can be solved by projecting onto the image of gradient. Finally, a minimal norm solution is given by this. Here is the Moore-Penrose pseudo-inverse of the graph Laplacian. By this definition, sinks are locations with higher potential, and sources are locations with lower potential. Distance matters in studies of migration data. We represent the distance information by the weights. In practice, long-distance moves are rarer, so we downweight edges that rarely see traffic. To be exact, we evaluate the distance deterrence by the frequency of migrations, and use them as weights for unobserved migration pairs. This lets neighbor-to-neighbor flows dominate the potential, conforming better to human mobility realities. Okay, but what happens if the distance factor is neglected? If we set all weights equal, our potential analytically collapses to net migration. This means the potential is an extension of net migration, explicitly considering the distance factor. Using this method, we present the results next. First, we answer which municipalities are livable from the young migrants' votes, with their feet in Japan. We evaluated the potential of Japanese municipalities for two focal groups. Second, we answer, what factors are important for livability? Using the potential as the dependent variable, we perform a regression analysis to examine the factors that determine the livability score. The third point is the connection to the previous studies in urban economics. I skip this point today. Here I explain the migration dataset and Japan's local governance. A municipality in Japan is the lowest level of government. Municipalities have their own elected mayors responsible for local administration and services, and a city is a type of municipality. We use public datasets in Report on Internal Migration in Japan, derived from the basic resident registration. The datasets summarize the number of migrants between municipalities, from the beginning to the end of each year, classified by age and gender. In this work, we study the report in 2019 to exclude the impact of the pandemic of COVID-19. There are 8.3 million migrants among municipalities. We focus on two specific populations in the dataset to discuss on the sustainability of the Japanese municipalities. First, as a proxy of families with small children, we focus on the children aged from 0 to 9, because family structure is not described in the dataset. Second, we focus on the women aged from 20 to 39 years, as reproductive-aged women. Here is the potential landscape for women of reproductive age. Warm colors, reds, are sinks attracting the people. Cool colors, blues, are sources where people leave from. Metropolitan cores, such as in Tokyo, Osaka and Hakata, shine brightest. The right panel focuses on the Tokyo area. The green border represents the metropolitan area of Tokyo, and the black border shows the special wards of Tokyo, known as the core of the metropolis. Here is the potential landscape for families with small children. Compared with the previous potential landscape, inside of the special wards of Tokyo tend to be blue in color. Families with small children leave from the metropolitan core toward the suburban belt. The potentials between these groups were very weakly positively correlated, or almost uncorrelated. This indicates that these groups will have different preferences for livable cities. Then, we classify the municipalities by this scheme. We performed the statistical detection of significant sinks and sources of migration flows, which are tested to have a higher or lower potential than a counterfactual null model. There are 3x3 classes, sinks for both groups, sinks for one group only, sources for both, and so on. The color-coded grid on the right of the slide summarizes that taxonomy. Zooming in on Tokyo, Panel C, and Kansai, Panel D, we see spatial segregation. Green-colored municipalities are the areas where reproductive-age women migrate into while families with small children leave. These green-colored areas are seen in the center or subcenters of the metropolis. Warm-colored areas are the sink of either of the groups. The warm-colored areas are often seen in suburbs, but municipalities in the suburbs are not always sink. There are several interesting exceptions. For example, in the special wards of Tokyo, the Bunkyo ward is red and attracts both groups. Bunkyo is known as a city of education. The University of Tokyo and other universities have their campus in this ward. What factors determine such differences among municipalities? So let's go to the next slide. We performed a regression analysis as the first step toward understanding what factors are important for livability. This is the setup of the analysis. We use the evaluated potential as the target variable. We select several explanatory variables related to income, rent, price, and various types of amenities, following previous works. We also selected the variables of public services and institutions by local governments, such as schools, hospitals, and libraries for future policymaking. As controls, we used the size of municipalities and region-specific variables. Here is the result. Some factors were significant for both groups. In particular, human capital has been argued to be a relevant indicator of urban growth, and was significantly positive in our study. Here, human capital represents the percentage of graduates over the age of 25 years. This variable would be a proxy for skilled and adaptive workers relevant to the productivity and economic growth of cities. The student-teacher ratio in elementary school also had a significant positive effect. This means that a higher student-teacher ratio is evaluated positively. However, a low value was considered beneficial. In the Japanese educational system, an elementary class has a maximum of 35 students. For large schools, almost all classes have the maximum number of students. However, classes with few students are often seen in small schools in depopulated areas. Therefore, this ratio can serve as a proxy for school size. The mean commuting time was significant, but had different signs for the two groups. A negative sign for women of reproductive age means they prefer a closer municipality to their workplace. On the other hand, it was positive for families with small children, and it means they prefer a more distant municipality. This is consistent with the observed preference in previous slides. Several factors were significant only for either group. For example, we examined the effect of large-scale retailers following the discussion on a consumer city. The variable had a significant positive effect only for women of reproductive age, and consumption amenities would be vital to them. This slide shows regional dummy effects. We set the baseline to the Shikoku region. It is the gray region in the right panels. Both groups had positive coefficients for the Hokkaido region, the North Island. Okay, let me summarize my talk. In this study, we proposed a descriptive metric of the livability of cities based on the migration flow of people using the unique decomposition of the combinatorial Hodge theory. As a case study, we applied this method to the data on migration flows between municipalities in Japan, and evaluated the livability scores for two demographic groups, families with small children, and women of reproductive age. Then we categorized the municipalities by identifying the significant sources and sinks of both migration groups. This classification clarified the characteristics of municipalities. We performed regression analysis and found livability is heterogeneous. Several factors were differently related to the scores of the migration groups. Therefore, there is no one-size-fits-all livable city. But, local governments in Japan often just copy each other's policies. Municipalities must decide which demographic they aim to court and tailor transport, housing, and public service packages accordingly. Thank you for your attention. I welcome questions and discussion.